Hey everybody. Now for something a little bit different. We are basically done with supervised classification finally, after looking at naive Bayes and KNN and decision trees and neural networks, all for classification purposes. We're going to turn to something a little bit different, which is the notion of unsupervised learning. So let's take just a quick look at the handout here. So the classification tasks we were doing were considered supervised learning. So in supervised learning, you have a training set where you know what the answer is ahead of time. So you know which ones are spam and which ones are not. Which ones are high quality wine, which are medium, and which are low quality wine. And then you give those training labels, you give that training signal to the system, and it forms its theory, and then you test it. But when you test it, you withhold the labels. You still know what the right answers are, but you see if the system can get them right on its own. So that's supervised learning, specifically for classification. Now we're going to look at unsupervised learning, one version of it. In unsupervised learning, there's different tasks that you can do, but the basic idea is you don't know ahead of time. You don't have a labeled data set. You don't really know what you're looking for. You want to explore the data in an unsupervised way. You don't tell the system much about what it's looking for or what the correct or incorrect answers are. You get the system to explore it and find interesting regularities in the code for you. Okay, so one of the things that is used a lot is automatic clustering. So the idea there is it's a little bit like KNN in the sense that you can imagine all the data that you've got, whatever it is, all the data points are scattered across a multi-dimensional scatter plot, and you're trying to see if you can find natural clusters, of those points. Where if you wanted to form 10 clusters, what would those 10 clusters of points be? So you're kind of grouping them based on distance, but you're doing it not blindly, not with any preconceived notion of what belongs in what cluster. Okay, so that's automatic clustering. Here's some examples of the use of automatic clustering, and there's links you can click on to read them. So Pizza Hut, there's an article there on how Pizza Hut breaks its customer base into what it calls segments, but clusters, so that it can target each cluster with customized advertising. So that's, a mildly evil use of machine learning, separating and identifying clusters of like customers so that you can target them for particular things. Okay, so there's a lot of machine learning based on that, how to sell people stuff, how to set prices, and so on. Netflix is another one, slightly less evil maybe. I don't know, use of machine learning. Evil's a strong word, but it divides its users into taste communities, and then it recommends things to them. So it's still selling stuff to them really, but in a different kind of sense. It's trying to keep them around by suggesting things for them to watch, keep them paying their their monthly fee. So it divides its users into taste communities based on what they've watched, based on similarities between their viewing habits, and then it uses that membership to customize its recommendations. So I see you're in this taste community, and you haven't watched this thing yet, which other people in your taste community have watched and clicked on that they liked it or whatever. So I'm going to recommend that to you. It also does a lot of clustering around sort of natural categories that it finds in the data. So, movies that are like, Die Hard will be a category. And also very specific types of movies, romantic comedies with a strong female lead will be a cluster. So there's all kinds of clustering going on in Netflix. And then Google News, and unfortunately this example doesn't work anymore. Last year it did, but Google apparently has changed the way that it does its news search. So it used to be that you could go into the news section of Google and search on something like election, and you would get kind of a lead article and then a bunch of other similar articles kind of bulleted underneath it, and then you get the next one and there's a lead article and a bunch of other similar ones. So it's clustering the news articles and sort of recommending to you the one that it thinks is the best, but then showing you the rest of the cluster. It may still be doing that behind the scenes, and you can still read here about how it did that. But now it only seems to be showing you one news article at a time. So I wouldn't be surprised if it's still clustering and then maybe just throwing out the really similar ones, if they have all the same text in them, if they came from the same newswire source. It doesn't want to show you 10 of those that are basically identical. So I think probably it's still doing it, but it's throwing away most of the cluster and just showing you the most representative one. But it's too bad because you used to be able to actually see the clusters, which was was cool. But that changed sometime this year. And I did a big search of, there are other search engines out there. We all know about Bing. I don't know if you know about DuckDuckGo and Swiss Cows and what else did I find? I can't remember the name of all of them. I tried about 10 of them, but they all behave just like Google. They're all taking their cue from Google, so they don't show their clusters either. But anyway, it's using it. So there's different approaches, but there's always a distance calculation. And the one that we're going to look at is one that makes use of something called k-means clustering. Okay, so it's got one parameter in it. The parameter specifies the number of clusters you want to form. It's easy to implement. It tends to be a bit slow, and it doesn't always find the optimal solution on the first run. So you usually have to do a number of runs. Now I have some code that shows you how this works, which I think I'll just fire up that code. So kmeans.py is in the code for this week. It's not actually using sklearn. There's some stuff in the comments here about how to use sklearn, and we will look at sklearn in the next video. For now, we're just going to use this data. What this is so there's a k-means algorithm here. It's a home-brewed, based on a published source that I found, a home-brewed version of k-means, and I've hacked into it so that we can watch it go. Normally, you don't get to see a picture of the clusters as they form, so we actually get to see the algorithm run. So I'm just going to run the code, and then this gives you the explanation here. There's a couple of data sets. So let's do load dataset testset.txt. So that gets us our data set, and we can look at it. There it is, for what it's worth. Then there's the k-means algorithm. So what we're going to do is it has two return values, centroids and assignments, and I'll explain what those mean in a second. I'm going to call the k-means algorithm with data. I'm going to say 4 clusters and show plots equals true to make it show kind of what it's going through as it does it. So it's going to pop up a bunch of graphs which we can look at. This data set, this test data set, has been specifically curated so that it works well for 4 clusters. It's a 2-dimensional set so that we can view it, and it's known to work well with 4 clusters. So let's take a look at it. Okay, here come my plots. So it looks like it needed only 3 iterations. Often it needs more than that, but this time it only needed 3. So this is the data. So let's take a look at this graph over here, plot 1_1. So run 1, iteration 1. What it does is these black points are what are called centroids. Okay, so it starts, I said 4, so it randomly chooses 4 locations within the range. So it'll measure the range of the data, the overall range, and then it will plop down these 4 random centroids. And you can kind of see how the data is clustering. There's a cluster here, there's 4 clusters, and it got pretty lucky with where it randomly placed them. Okay, then the first step is it assigns all of the points to a centroid. So that's what all the coloring and shape is about. So the blue, you can kind of see the blue points here were all assigned to this centroid because we did a distance calculation from, say, this point here to all of the centroids, and this one was found to be the closest. So that means that this point belongs to this centroid. So that gets us our clusters. So you can kind of see there's a cluster, 4 clusters, 1 for each centroid. That's the first step of the algorithm. Generate the random centroids, k of them, and then assign to those centroids to create the initial set of clusters. And you can see there's some issues here. Like it kind of looks like maybe these points belong to the purple cluster, really. Maybe they should be grouped in here, but that's just not the way it's worked out. So then the next thing it does, and this is where the k comes from the number of clusters, means, the k means, mean means average. So what it does now is it moves these points. It's going to say, so take a look at this centroid here. It's going to move it into the middle of its current cluster. So after it's assigned all the points that belong to that centroid, it then takes the average x coordinate and the average y coordinate of all those purple points, which is essentially the middle-ish, middle, quote unquote, of this thing, and it moves the centroid there. So there you go. You can see it's moved there. This one has moved just a little bit, moved over here because there's some outlier points here. And this one moves quite a lot down into the middle of its points, and this one moves over here into the middle of its points. And then after it's done that, it repeats. So then it goes through and reassigns every single point based on distance. And now that the centroids have moved, you can see that these points here, which used to belong to blue and green, have been reassigned to this centroid here. This one I think has only lost points, and this centroid looks, this cluster looks the same, even though the centroid has moved. It's got all the same points in it. And then it does one more iteration where it adjusts the location. You can see the centroids move just ever so slightly. This one moves back a little bit. This one doesn't look like it's moved. This one moved maybe down a bit. And then it reassigns. And at this point it stops because nothing has changed. The location of the centroids from this picture to this picture have changed, but the clusters haven't changed. The clusters are the same. Okay? Now if we run that again, let's run it again on the same data set. Oh, it only took 3 this time as well. Oh, but this is an interesting one. Okay, now that first run seemed pretty good because again, visually it looks like there are supposed to be 4 clusters here. When this one started, if you take a look, it didn't choose very well. It randomly chose these 4 clusters. Now we can see the data, so we know it's not a good choice, but the system can't see the data in the way that we can. So it chose these 4 points here, and then assigned, so there's a big green cluster here, a red one here, and a big purple one here, and a blue one here that belongs to this point. Then it moves the centroids over, so this one moved way over, this one moves way over, so that they're in the middle. Again, by computing the mean, it goes through each dimension of all the green points here and computes the mean, and then puts the centroid there. So we end up with these centroids. And quite a bit has changed here. Actually, I think nothing about the red or the green cluster has changed, as far as I can see. But the blue cluster and purple cluster have exchanged quite a few points. So it goes through another iteration. It moves the points to the center. These ones don't move because they didn't change anything. These ones move over, and this time nothing changes, so it stops. So these aren't the most interesting runs here. Let's try one more. Maybe it'll go for a few more. There we go, that's more fun. So this one has a lot more. 2, 3, gotta bring them all up. So 7, 6, 5, 4, 3, 2. Oop. It's going to make it hard to compare because I just changed the shape of that one. That's pretty close. So there we go. So it starts with these 4 points, and then it starts moving and changing the clusters. And actually this one's pretty cool because look at this cluster here. So right now, because this point's the only one over here, it basically owns this whole side of the data. All those clusters all these points are closest to that centroid. So it moves way over, and ever so slowly, this point moves over too. So as it's giving up more and more points to the blue cluster, it's moving over, and eventually it moves to where it needs to go. So even though we started kind of suboptimal, we end up with 4 pretty good clusters. So that's pretty good. All right, so let's go take a look at, this walks you through the explanation of what I just did. So again, it's using my same code, which I gave to you. Here's a starting point. Here it is after they move the centroids into the mean location, into the average location, and I'm circling points that have changed. So these used to be blue, now they're purple. They're not the only ones, though. There are other points that have changed color as well. And then, you know, it moves again, and it keeps going. This one went for 6, so between here and here there were no further changes to the clusters, and it found a pretty good set of clusters. Okay, so as you can see, you have to run k-means a few times and look for the best clustering, because it starts with a random set of points. It can't know in advance where it should put the points. It starts with a random set, and so sometimes, just the way the algorithm works, it ends up in a good state, and sometimes it ends up in a bad state. So we need to know, how do we measure that? So here's an example of a bad one, right? I mean, we know it's bad. Again, we know it's bad because we know that there's supposed to be 4 clusters, but this one turned out this way. Okay, and we also saw in my runs there were some bad ones as well. But the question is, I mean, we can eyeball it and say, yeah, that's no good, but we need some measure of cluster quality. And so what we do is we use this thing called the inertia, or the sum squared error of the clusters. So what we do there is to measure the quality of this clustering, we take the distance from each point to its centroid, so distance from here to here, distance from here to here, distance from here to here, and so on. We square those distances, and the effect of squaring them means that outliers like this one, which is far, will have a big impact on the overall measurement of error. So this error will be quite large because the distances from here to here are quite big, and when they're squared, they're going to get even bigger. They'll grow by the square of the distance. We add them all up together, and then that just gets us a number, and we can use that number. That number on its own doesn't mean a whole lot, but when we do multiple runs of k-means and we compare all of those numbers together, we can use that number to find a good, the best solution of all the clusterings that we tried. Okay, so like say you do this and you end up with a sum squared error of 1,000. Is that bad or is that good? You don't know really. And if you think about it, the more data you have, the higher your sum squared error is going to be because you're just adding up all the distances. So if you have twice as many points, you should expect your sum squared error to be twice as high. So on its own, one sum squared error is pretty meaningless. Also, the scales. These numbers go from about -5 to 5. What if they went from -1,000 to 1,000? Then again, the sum squared error would be way bigger. So on its own, the sum squared error doesn't mean anything. What you want to do is do multiple runs and compare one sum squared error to another. And you can see it over here. So if I go, so I've got C, so this algorithm, which ended up with this solution here. Wait, let me move this over a little bit. We'll move this here, move this over here. So this sort of homebrewed k-means algorithm, it returns a set of centroids. So C gives us an array of points that represent the centroids. So 2, 3 is this centroid here, 2, -2 is this centroid here, and so on. You can match them up to the centroids. And then A are the assignments. So in this testing data, this is kind of an ugly array, but the first point in the list was assigned to centroid 0, so assigned to this centroid. The next one was assigned to centroid 2, which would be this one here. So each of these rows is for a point, and in the first number here tells you what centroid it was assigned to, and the second number here is the square of the distance from the original point to that centroid. So what we can do is, for this solution, which we know to be quite a good one, we can do we just want the first column, and we want to add it up. So that gets us our sum squared error of 149 for this solution. Then if we run it again, let's see how this one does. That's a pretty good one too. So it's basically the same solution. So it's about the same sum squared error, 150. I'm going to run this a few times, and I'm hoping that we'll find a bad solution. That's plot 4, 4. That's still a pretty good one. Yeah. Oh wait, that was actually plot 5. Like that. Plot 6. Still looking good. Let me close all these. I'm gonna keep going till I find a bad one, hopefully. Oh well, I'm not gonna be able to show it to you, but so you can try it on your own. You can try it at home. So, for plot 1.6 here, the inertia, you'll just have to take my word for it. The inertia here is about 150, which jives with what we were seeing. We were seeing numbers of about 140, 150 when we got more or less the same solution each time. This one here, which represents a bad solution, has an inertia or a sum squared error of almost 500. So it's quite a bit different. You do 10 plots, 10 clusterings. You get most of them around the 140 to 150 range, and one that's 500. You take the smallest one, and you're going to be good to go. How do you know what the right k-value is? You don't know your data ahead of time. You're clustering in order to explore it. That's the whole point of unsupervised learning, is you don't know how good it is. So here's some examples. We might start with k equals 2 and get a clustering like this, then k equals 3, and then k equals This one's k equals 5, I think. We've seen some with k equals 4. How do we know which ones are better? Sometimes, you know, here there's a little bit of a dark art here. Like you may know in advance what the number of clusters is that you want for some reason. You may have an optimal number in mind because you may think that the data naturally forms a set of classes, so you might have something in mind for that. But you may not know, and it can be very difficult to figure out what the best k is. You might have to actually do some experiments. So if it's a recommender system and you're clustering customers, you might start with 100 clusters and start making recommendations, and then just see what the quality of those recommendations looks like. Actually design a true experiment where people are maybe rating, or an experiment, maybe not a true experiment, but an experiment where people are rating the quality of the recommendations. Or you might just check to see how often they click on them, and then run that for a while, and then try 1,000 clusters and see if your click rate goes up or down. Sometimes you have to do stuff like that. If you're lucky, your data has a natural cluster point. So the data that I created does have a natural cluster point. And when you graph, so this is your k here. For k equals 2, my sum squared error is up here. For k equals 3, it's here. For k equals 4, it's here. So every time you do this, your sum squared error will go down every time you add a centroid, right? Because if you think about it, that means that there's more centroids, which means each point will, on average, be closer to one of the centroids because there are more of them. So your sum squared error will keep going down no matter what, but you might find what's called an elbow in the graph here. So for the fake data that I showed you, you get a very rapid decline to k equals 4, which is the natural cluster point of the data, and then it continues to decline but very slowly after that. So that just looks like an elbow. That's a pretty clear one. Most of the time you won't find an elbow in your data, but it's worth looking for it. So we'll be doing that in the assignment, looking for an elbow in our data. Okay, so you can do that. This is a graph that was drawn with PyPlot. And the other thing, I skipped over this, making predictions. So the output of the k-means algorithm, it has k centroids. They're labeled 0 through k minus 1. And when you get a new data point you haven't seen before, you just compute its distance to each of those centroids to decide which cluster it belongs to. So if a new customer comes in, you assign them to a cluster, and then you can make your recommendations based on the cluster that they're in. Okay, so I hope that was fairly clear. I want you to do a couple just paper and pencil exercises just to make sure that we get this. So we got a clustering task with 2 features. You ran your k-means code and you ended up with k equals 2, and you got these 2 centroids. So I want you to assign each point to one of the centroids using Euclidean distance. You could, of course, use Manhattan or some other distance or similarity measure, but Euclidean distance is the most common, so we'll just use that. So figure out which centroid does each of these points belong to. And then I want you to compute the inertia, which means just the sum squared error of those things, and compute the overall inertia of this solution. So I will do another video where we'll take a quick look at how to use k-means in sklearn, because that's the one that you're going to use for the assignment, and then we'll take a look at the assignment itself. All right.